see everybody today. Couple announcements. Midterm on Wednesday. This is intended to be a 50-minute midterm, so show up 20 minutes early. I'll distribute the test to you face down. We'll turn over the test and get going. Most of the midterm will be very much like homework. Maybe an extension to a problem in the homework. See if you thought about it enough. It's not intended to be a bunch of curveballs. And so, similar problems that we've seen throughout the class, but we've covered a good amount of material. And a lot of it we're going to dive down into even further. So I'm sure there are questions about everything. If you're sick, send me a note, but it is intended to be in class. This is an in-person class. So we're trying to accommodate everybody with everything, make everything happen. But you gotta let me know your state for this. This is very important. So that's the one day I've said, gotta be. Of course, if you need to quarantine, that's a different story. Okay. I usually run a yes, no, maybe session. I usually do it during my review sessions. I'm going to do it a little bit different this year. I'm going to do it in class on Monday. And the idea is that I'm going to write on a piece of paper or several pieces of paper, yes, maybe, no. You make 3 columns. And what you can do is you can ask me what's on the test. And I'll answer you. So it only works if I make the test, so I'll make it on Sunday. A lot of it comes from the homework. So you're going to work out a Jeffries prior, something like that. And then I have a little trick in there to test whether or not you know what a Jeffries prior is. So I ask you another question about a parameter, something like that, and I ask you for maybe the Jeffries prior of that. There is a very long-winded calculation, and there's a very quick calculation. And so that's kind of what I'm aiming for. I would like this to be a 2-hour test, but 50 minutes is what we've got. We've got a class piling in right after. Anyway, Monday for about 30 minutes, we'll spend time doing that. Any questions? Do you want to know something on the test? I'll answer in this call format. Jess?
So you mentioned in the review session that there will be like 5 questions, and we have 15 minutes, so like 10 for each.
Yeah, that's the math. So on average, 10. So if you're good at the homework, it's like bang. But if you're still at the state on the homework where you're like, I can't recognize the conjugate prior for an exponential distribution, it's gonna be a rough test. So it's really, the thing I can tell you to spend your time on is know your distributions, know things like their expectations and whatnot. There's some obvious stuff I'm going to ask you. It's very likely I'm going to ask you to identify a conjugate prior and maybe work through a posterior predictive distribution, stuff like that. The calculus is not intended to be difficult. So I'm not going to test you on, do you remember how to integrate this crazy function like here? If anything looks like a crazy integration that you have to do, you'd probably be able to do it very quickly if you know that normalized constant for something. So, I think the problems, yeah, I get it. First time on the homework, it takes you 8 hours to do a problem. But I think it becomes 10 minutes after you know how to do it. So we'll see how it goes. I've done this before. It works. It's okay. I'm always handing out extra credit as well. So I'll identify extra credit problems as we go. I usually don't write them down for you. I just tell you. I write it down maybe on a piece of paper. So I'm not going to have a list. You have to be astute enough to know that I've offered you extra credit. And you have to know how to go again. So there's one sitting for you online right now. Go to my code. You have to do this for your homework anyway. And fix that one decision rule in there. Send me that snippet of code. So when you come to me and say, I've done it, how do I get my 5%? I'll say, just send me that snippet of code. I'm gonna plug it in and see if it works. So if you can write in R or C or Java or whatever you use, you can write it in MATLAB. So pretty basic syntax. I'll keep supplying those problems to you. Keep in mind, you have to do that for your own homework anyway. It's when you end up proposing the precision, you're going to need some proposal, and I'll give you another piece of the hint. The proposal I used, the truncated normal, is not symmetric. There's a handout online, and it tells you what to do. It even has the code. It has it inputted in R for you. And it runs an incorrect sampler and a correct sampler. And at the end it says you can't really tell, but I think it's an interesting thing to just look at. Go in there, try to see what's going on in my code. I have everything on a log scale. I'll be walking you through that code later too. So you don't need to do it this weekend. Study for the exam. And later on, if you feel like you need some extra points, you know where to go. I'll probably add together maybe 50% midterm points through extra credit throughout the rest of the semester. Okay. Yes, no, maybes on Monday. 10 minutes per problem on Wednesday, on average. There'll be some easy problems on there. I would say the problems are easy or medium. So the easy ones are where I can really grade you. So if you can't get that, oops. So anyway, I've got some classics that take about 2 or 3 minutes to solve if you know what you're doing. Homework that was supposed to be due today can be turned in on video as well if you need more time. So there's the announcement to everybody out in virtual land that if you missed it, I've addressed you. If you sent me an email last minute, you're off the hook. So let's not make it a super habit, but I just want you guys to stay afloat, but I understand this is the busiest time of year. Okay, any questions before we move back to random effects, hit samplers, Wisharts distributions, a lot get piled into this lecture. Okay, so my notation is just a little bit different. It's in the paper that's online that we looked at last time. But essentially, this Delphin and Smith early model that they used really to exemplify Gibbs sampling. The Gibbs sampling paper doesn't have the scientists on it. It's a very typical strategy. I really like this stuff. I like working on applications, seeing new problems that exist, and then writing a methodology paper. So they did really well to get their money's worth out of this thing. But basically, this model is a motivator for Gibbs sampling. This is the first example that everybody got to play around with. This is for statisticians in Gibbs sampling. I just want to point out, Delphin and Smith did not invent the Gibbs sampling. They generalized the concept. So they wrote it down with like general distributions. It had already been done in specific contexts. So in the 80s, I think it's Gehman and Gehman get credit, 2 brothers over at Brown University, and they were working on lattices. So they're playing around with lattices, and they basically incarnated Gibbs sampler for sampling these lattices. The lattices represent charges, pluses and minuses, and so they're looking for whatever the stable distributions are. What are the samples of these lattices out of some model? It was an Eisen model that they were playing around with. Gibbs had done something similar to this as well, way back when. So 20 years previous to that. Delphin and Smith show up, and they write this general paper. And in my world, there's a lot of times people say this is the most cited paper in statistics. Every little subfield has their paper that's the most cited one. Does anybody know what the most cited paper in statistics, generally speaking, is? Which one? Yeah, maybe. So that's possible. I hear people sometimes say it's like a Kaplan-Meier paper, but survival analysis, people will say, oh, it's that paper, and it is cited a lot. I've gone to Google Scholar. I don't know if it's adequate for answering this question. I'm not sure we can ever really know the answer to this question because it's constantly fluctuating and moving. But the Gibbs sampler paper, it's one of the paramount papers. It really makes Bayesians practical. So we can finally solve problems like the one that's presented here. Okay, so again, just to recap, WIT is the rat eyes weight at week T. Okay, so this is a pretty nice data set. It's nothing too, it's pretty well manicured. All rats make it to the end of the study. So They make it all 30 weeks, so it's not a survival analysis or something like that that would be hard. So this is just kind of modeling kind of the temporal trends. This isn't like what I would call a true time series model, but it's okay. Idea is that rats each have a set of rat parameters. So the intercept is going to tell us about the rat coming in at the initial state. So their initial weight, and then the leading coefficient here, beta I, that's going to be its propensity to put on weight or lose weight throughout the study. The big question exists as to whether or not these two parameters are correlated with each other. So you want to make problems easy, don't build correlations into anything. You want to make problems harder, build correlations into everything. So that's about 50% of my job, is I build associations between parameters, and it gives us better inferences. We're able to do this now because of computation. So I guess back in '89, this was a pretty difficult problem. And there's only one correlation that's really being modeled here. So the big model of correlation in these two parameters, I'm going to call alpha I, beta I, theta I. And I should probably say that this is transposed right here just to be consistent in my notation. Theta I is a column vector. And this is called a random effect right here. So the rat's parameters are random. Other random effect models happen when you have like these group settings and you think that there might be some sort of type relationship in that group setting. And then there's many groups. So you might see this if you are studying chimpanzees or something like that out in the wild. You're making a measurement, but you might know their relationships between each other. So chimpanzees that come from the same family tend to be more alike. And so there would be a random effect in it. What's driving all of that? I guess it's genetics. So these are genetic parameters. They're really not. This is a statistical model, but these are a proxy for the rat's genetics. I can think of other examples of random effect models. Let's say you have a whole bunch of STAT 101 classes. So let's say you've got 50 STAT 101 classes at the university. This is probably the Wikipedia example. And you've got 5 instructors, and they each teach 10 classes or something like that. Let's say there's 50 classes. I'm not sure how many I said there might be a whole distribution of the scores on midterms across all of those classes, but you would expect to see some grouping because of the instructor effect. So there's random variation because of the instructor themselves. So you might want to untangle those parameters and say there's specific parameters for the groups. This is not a Bayesian idea, although I will say, if I didn't tell you and I just walked in and I said, this is a prior on my theta i's, you just roll with it. But non-Bayesians do this as well. Keep in mind, when we go to update these alpha I parameters, we'll do something that looks very akin to Bayes, and we'll multiply by this random effect distribution. If you just slot in that word as a prior, you'll be able to do the calculation that way, but that would be the wrong terminology. Okay, so the whole idea is to model this covariance. So we want to learn this parameter right here, what's the covariance in the population. Here's the population mean for all of the rats out there. We're going to estimate that, but we're also going to estimate the rat-specific parameters. I'll mention also that there's a variance in this model, and that variance is common to all the rats. Why did they do this? I guess they thought the variance was common to all the rats. Same sort of variation in there. Is it possible that they all have their own sigmas? It is. So I wouldn't know the answer to this until I modeled both of them and I compared those two models, how well they performed. To do something like look at likelihood ratios between models, Bayes factors, we'll get into that soon enough. But there's a lot of ways you can compare the performance of two models. My favorite comparison is not fit measures, but predictive measures. I like to see if the models are able to predict. That's my own personal preference. When we get into model comparison, I'll talk about that. Okay, so we'll trust Gelfand and Smith that maybe they did entertain models where that variance was different for each of the different rats. Now, I will say, you could start saying, well, maybe at every time point, the variance is different. But you've only got one data point for each time point as well. And so you wouldn't be able to index that also by time unless you built some constraints into the model. So building too many effects into the model might over-parameterize your model, maybe, so you can't estimate anything. If we did model this with a sigma I, and the sigma I for all the different rats was the same, basically we would be diffusing our distributions a little bit. We'd be losing some power in our analysis. So if it's a common parameter, then we would want to model it as a common parameter. Okay, we'll go with the model. They wrote this down for us. So my next question for this, since we are Bayesians in this class, is which priors are we going to adopt for this? So I should probably say which parameters need priors before we even talk about the priors themselves. So the parameters that we need priors on is beta naught, sigma, and I'll say or sigma inverse, or some function of sigma. I'll talk about that in a moment, why I prefer actually modeling sigma inverse in my own practice. And we also need a prior on this parameter as well, sigma squared. And I don't ever like to work with sigma squared. I like working with phi for perfectly arbitrary reasons. I like gammas. But if I was working with somebody else and they said, no, we've got to do this on sigma squared, I might transform my answer at the end of the day. If they said no, I don't even want you to do that. I'm going to watch how you operate. I don't care what your answers are. I want you to do it my way. Then I would use an inverse gamma distribution. Sometimes you'll see it in the Kelvin and Smith paper that we're discussing, they use inverse chi-squareds. So chi-squareds are subs of gammas, so they fit into the gamma family. So there's special parameterization of it. And so in there is how to fall. So I don't talk about chi-squareds too often. I usually talk about gammas, and then I'll build in the restriction. We've done this before with things like T's and Cauchys. So Cauchys I also call as T1s, and usually I work out all my answers in terms of T arbitrary degrees of freedom, and then later I plug in one, something like that. Okay, what parameters would you choose on this? We know the answer here. We'd make the analysis easy if we pick the conjugate prior. So maybe a normal. And that's what they did in the paper. And they don't pick any old normal, they pick a specific normal. So they're working with a couple scientists. They don't have a ton of data, so they want to kind of push in some things that they know, and they parameterize these distributions. So they build in something right here. Let's just call it this. So remember, this is a 2x1, two-dimensional right here, because that's two-dimensional. And so this is a 2x2. This, we just had the whole discussion about that. We'd probably think this is a gamma. With a couple parameters in there. And if you're super curious why they picked their parameters in that paper, you would have to read the paragraphs right around it. I kind of find it unsatisfactory. You know, when I always read through these things and people are like, we picked this, and it's usually like a sentence. And it's like, say more about that. I want to know more. So, subjectiveness. So they don't like to tell you. I got a scientist that told me that this was okay. And I hear myself saying things like that, but I like to blather on 10 reasons for picking something. Certainly when I do something and I arbitrarily pick parameters, or if I have subjective cause to pick parameters, I never feel good about giving people one reason to pick it. I always need to give them two. So I think that that's just good practice. You can do what you want. We're going to be talking about the Wishart distribution. And I'll just let you know, for this parameterization right here, we have modeled this by a Wishart. So Wishart is conjugate. And we'll see that in a moment. It's easy to get confused on this. Sigma inverse Wishart is conjugate. For sigma, the inverse Wishart is conjugate. It's exactly opposite of the gamma. So just to build in something, just store one piece of memory, a spot in your brain, and you try to remember that. So I think when I learned this, I messed up like 3 or 4 times. So I was using the wrong prior in my homework for the first couple of attempts of this. You have a homework problem that you need to work through, and I think I cut it on this scale. So you're going to be using the inverse Wishart in your homework. I'll walk you through both distributions. You will see people use both of those depending on what their intentions are. I provided a handout, 2-page read on the web page, and it tells you about precision matrices. So the zeros in precision matrices tell you about conditional independencies, and that's all laid out for you. And that has a lot of applications. So if you think about the stock market or something like that, people want to figure out what is conditionally independent of what and group things together. So they'll create portfolios this way. So I know quite a few people working in hedge funds, and this is standard practice, is to model covariance between all the stock prices. They'll have some time series model, but they'll also have some covariance running in there, and they'll model that with some very high dimensional Wishart distribution. And then the whole trick is to do the calculation, do the computation. It's actually a difficult problem. Those classes of models are called Gaussian graphical models, if you want fancy names for all this stuff. So, where's the graph? It's in the picture you draw about the conditional independencies, but it really is just a model. Okay, Wishart distributions look like this. So let's just think about this for a moment. Let me tell you what all these parameters are. V is a matrix. It's positive definite. So there's a constraint on these matrices you get out of this distribution. So this is a distribution over matrices. So I plug matrices in to this formula right here, and I get a number out of this. This is just a density function. So it tells me which matrices are more likely than other matrices. So they tend to center around a parameter that we're going to have as an input into this. So these are my hyperparameters, or my parameters. If I use it as a prior, we would call them hyperparameters. They don't center around omega. They actually center around gamma times omega. And so quite often, I will put a gamma right in here. So I'll just put this in braces right here, and I'll drop a gamma right there. And so if I drop that gamma, which is a scalar right there, then the expectation becomes just omega. So then I can interpret it that way. So I like to build interpretation into my thing, and then I have to figure out this diffusion parameter. So if I parameterize it again, like PV given gamma omega, and I write gamma right here, the expectation of V will be equal to omega. I'm not going to write it down like that throughout this, but I suggest that parameterization on the homework. So you'll just have to think about how you interpret these things. Why do I do that? So I can interpret this thing as the distribution. I'm centering everything around, and it turns out gamma is going to influence the variance. So how dispersed are these matrices that are centered around this thing, or under this parameter, just that. So gamma is a scalar. I'll point out omega is a conformable matrix. All I mean by that is that it's also k by k. So when I multiply it into the other matrix, I can multiply it. You'll notice also there's an inverse that shows up right here. So that matrix that I plug in has to be invertible. And you'd probably be surprised if I told you anything different than that. It just kind of means that you can't operate like that. So it's an invertible matrix. It's also going to be positive definite. For those of you that don't know, covariance matrices are positive definite. The inverses are positive definite. What does it mean to be positive definite?
So you're going to start positive.
That's one definition. All positive eigenvalues. So it's a pretty mathy definition, but that's true. So any others? You were trying to explain this to somebody. You said, well, it's positive definite. And they say, what does that mean? You say, the eigenvalues are all positive. Oh, thanks. So then you would say, go take a linear algebra class, kid. So in doing, I'm not even going to try fold with this. Basically means that your surfaces are convex in everything. If you had a covariance matrix that was not positive definite, it would have a ridge, a flat ridge running across it. It would basically mean that that normal didn't have a nice peak in it. So I like to think about it a little bit geometrically, what it means. So no ridges and everything. Zero eigenvalues would induce ridges. Negative eigenvalues all of a sudden flip the convexity of that space around. And so that's the way I tend to think about it. There's other definitions as well. So I might say positive eigenvalues. I might say a Cholesky decomposition exists. So if it's positive definite, then I can take V and I can write it down as the product of a matrix multiplied by its transpose. This is an if and only if statement. So basically the square root of the matrix exists. So I think we've talked about this a couple times. But this we might call V1/2. So that would be my notation for it. V1/2 isn't unique. There's a lot of ways to do this factorization, but this is an if and only if statement. But basically this, well, not basically, the square root of the matrix exists if and only if it's positive definite. And the reason I never really like to say the positive eigenvalue thing, because if you went to check that, that's the longest calculation you could do to check positive definiteness. So it's the hardest calculation you can do, is to get all of its eigenvalues. I need to get all of its eigenpairs. So you have to do a lot of calculation to do that. The Cholesky decomposition is the fastest way you can check positive definiteness. That's what I do in my code if I need to check, is I type in Chol, plug the matrix in, and if I get an error back, it's not positive definite, I should stop the calculation. I'll just point out in MATLAB and R's facilities, if you invoke a normal distribution in high dimension and you plug in that matrix for its covariance, it will check to see if it's positive definite. And so if you profile your code, if you keep using like the normal built-in PDF in MATLAB, it's going to do this long-winded calculation every single time you invoke it. And so if you ever are profiling your code and looking at the time of each one of the functions, if you use the built-in facilities, you'll see that normal PDF takes up an excruciating amount of time. I always write my own when I invoke it in a function. So it saves me days, especially if you're working in high. Right, Sierra?
Oh yeah.
Oh yeah. So everybody finds this out eventually. Why is this taking so long? Okay. Nice thing is that coding up your own normal PDF is pretty easy. What I always code up is the log of it. And I always operate on the log of it in my code. Do that instantaneously. Do that right. Okay, so basically the distribution right here looks like this times this thing. So the product of these two things. And all this other stuff right in here is normalized constant. So if I ask you to integrate over this distribution, if I ask you to integrate over the kernel of it, it will integrate to the inverse of that. So there's a problem on your homework that asks you to marginalize out a matrix. What does it mean to integrate over a matrix? It means to integrate over all of its elements. Because of the constraint in there, it's positive definite, and there's a symmetry right here. You don't have to integrate over every element. Think about a covariance matrix. The triangles are the same. So you're just integrating over one of those things. And so integrating over a matrix is just integrating over every element of that matrix. This right here is the P-gamma function. I'll write it out for you a little bit differently in a moment so you can see what it actually is. But basically there's a big product of gamma functions that appears. If you look at this kernel right here, you'll notice that that kind of looks like a gamma distribution. And if I did everything in one dimension, i.e. that thing right there is a scalar. This looks an awful lot like a gamma distribution. So I'd say this is the multivariate generalization to a gamma distribution. So powerful distribution that you can use. Wishart distributions, I trust this is the first time you've ever seen it, ever heard about it. But Bayesians play around with these things. Let me show you the inverse Wishart distribution as well. And I've written it down a little bit differently. I wrote down the P gamma function like this, just so you can see what it looks like. So basically there's a lot of inverses that show up. So the inverse of the matrix will show up in the form. My random variable is B again, just like in the other notation, but now it's B inverse right there. So I grabbed the two different formulations from two different books just to show you it appears differently and you kind of have to study it for a minute. So in the integration that you're going to be doing, you're going to, in your thing where you invert everything, you're going to be integrating over something that looks like this. And basically, your integral is going to be proportional to this part. This stuff is all just a number. So some number. This is the part that's going to have all your parameters left over in it. So what I've asked you to do on the homework is consider a dense covariance matrix that you're going to integrate out. Up until now, everything's been diagonal, and all we have to integrate out is d or sigma squared. So you're going to be integrating over a covariance matrix, and basically this is the answer to that integral. It's going to have all your parameters in there. I want to point out for this homework problem that you come up with, this is number 6 on the last homework. You're also going to need this identity to play around with. You're going to get back a distribution, and it's going to be in the form of a determinant. So that's all determinant right there. You're going to be like, I want it to look like a nice PDF function that I see in the book. And you're going to need to be able to turn this thing into something that looks more one-dimensional. Keep in mind, this is 1D. It's a determinant, but everything is being written out as a matrix. So here's an identity. This one is for determinants. Back in my day, if I got my homeworks that have this stuff in it, here's how it would go down. I have this determinant thing, and I don't know what to do with it. So you run around to all your friends, and you tell them about your struggles, and then one of them tells you they ran off to the library, found a book on this, and grabbed a matrix identity book, and found the identity that was necessary for it. So it's a time-honored tradition have everybody struggle and go to the library. So I'm just going to tell you what it is, but with this remark, go get yourself a matrix PDF on a list of identities. I have one on my computer. Every time I get a new computer, I drop that thing on there so I can just open it up. Maybe we'll post one for you guys so that you just have it. How do you prove all these identities? Just show that the left and the right-hand side is the same. How did people come up with it in the first place? You have to ask them. So I think it's quite difficult and tedious to work through everything. They probably went through painstaking details to come up with these identities. So here's the identity that we're going to use. And I'm going to write it down in a more general format, and then I'm going to say something about how you're going to apply it on your homework. So let's say this is X, B, X transpose. And I need to give you some dimensions on everything. So let's say this is K by K. So I know that this thing has to be K by K as well, if I'm going to add it into it. So let me just build in some dimensions. I'm going to say this is K by P. This is P by K. And this is P by P. Right here. So this one is P by P. This is K by P. This is P by K. And I'm going to say A and B are invertible as well. They're squares, so we're going to invert them. Let's say their E inverse exists. In your problem, the inverse will exist. This can be written down like this. This is the same. A inverse, B inverse. Right here. This is going to be a B inverse. A inverse over here. And this is going to be X transpose X. So you'll notice the swap on the X's. And you can check all the dimensionality of everything and it all works out. So that's a formula you're going to need to use. In your formula, it's going to so happen that this thing, once you do your integral, this thing is going to be a scalar in here. You're not actually going to have a number, a matrix in there. So when you end up applying this formula, and B is a 1 by 1, this whole thing right here is the scalar. And you can drop the determinant. Okay, so I'm not going to go through the whole homework problem for you, but these are things you're going to need to remember. So go back, rewind the video when you get to homework problem 6, and apply this thing to it. In your homework problem, these are going to be constants of proportionality. So these are going to cancel. You're just going to throw them away. So the whole problem you're going to be working with when you do this, when you integrate over the covariance matrix, you're going to induce a t-distribution. So just think about what we do when we work with that normal problem and we integrate out phi or sigma squared. What happens to that normal problem? It becomes t when we get rid of the variance. Same thing happens in problem 6. You're going to integrate against the covariance matrix or the inverse covariance matrix. The answers will work out the same. You're going to be using the inverse Wisharts though, the way I asked it. And what you're going to get at the end of the day is this, which is going to become a scalar thing, and it's going to look like the form of a multivariate t-distribution. So you want to look up what a multivariate t-distribution is, and you'll want to look up what an inverse Wishart looks like. In solving the problem, it's really just a bunch of pattern matching. Okay, so those are just some hints for you. We've said a lot. Let's just show real quickly that the Wishart is conjugate. So I'm going to work with a slightly simpler problem than the RAP problem and let you apply all this to the RAP problem for your homework. Oh, before we do that, let me help you out with another problem on the homework. Let's write down the likelihood for this model. So I think that's what we need to do. So the likelihood for the RAP model. It's how I always work out likelihoods. It's always the same thing. I write down the sampling distribution. So I got to just think about this sampling distribution right here. So how is this sample generated? The sample is W. So the likelihood is is going to look exactly the same as the sampling distribution on this piece of paper. It might be off by some normalizing constants. We can throw them away. We can keep them. I'll keep them around just for completion. So for each rat I, for each rat, they have a time series of things, and they're conditionally independent, each observation. So I've got a model for P, W, I, T, and they're going to be conditioned on the rat distributions. I'm going to write it down as theta I instead of alpha I, beta I. If you write this out linear algebraically, the problem's easy. If you write it out in terms of alpha I and beta I, and not using transposes and vector multiplication, matrix multiplication, the problem is really messy. So theta I, and it also depends on sigma squared. So that distribution right here is this equation. What is T? Well, I look over here, oh, it's a normal distribution. So that's what it is. And I would eventually write that down in parametric form. So for each rat, they have a time series. But this was generated from the random effect. I'm going to write that down. P theta I is conditional on theta naught and sigma. So for each rat I, this is their partial contribution to the likelihood. For all the rats, everything looks like this. Right here. So there's your likelihood function. If you want me to write it down parametrically, we can do that. So this is going to just be this normal distribution. We can write it all out. So this thing is just 1 over root 2 pi. There's a sigma in here. I'm going to make it a phi. So I'm going to plug my phi in. My phi's right here. So E to the minus 1/2 W I T minus, this is something squared. How should I write this thing down? This kind of has to do with these parameters right here. So this is, need some notation for this thing. I'm going to write it down like this. I'm going to say this is theta I transpose times 1t. That's just a vector of 1 and t multiplied by theta I transpose. That's exactly this. That's how I write that down. Make the problem real easy when you write it down that way. You could call this something if you wanted to. Get rid of that little indexing. Come up with another name for it. This will be squared right here, but I'll just plug that in there. This is going to have your sigma squared down here, which we called. So that's that part of everything. Check. That goes into this product. And this part is just going to be sigma, I'll say it's proportional to sigma to the minus 1/2, E to the minus 1/2 theta I minus theta naught transpose sigma inverse theta I minus theta naught. Binary problem. So there's your likelihood function. The pitfall on messing this up is getting these braces in the wrong place. So I'll point out, when I go to try to learn all the theta i's, I don't need a prior. It's already kind of sitting there for me, so it's already a random distribution. You can't make it super random by multiplying by a prior. So that wouldn't mean anything here. But if I wanted to figure out what my full conditional on theta naught is, I'd look for everywhere the theta naughts pop up. You'll notice this part of everything falls out. How many times is that being producted up? T times. Or sorry, the I times, the N times. Eventually I'll get the right letter. So this is being producted up N times. Doesn't have anything to do with this product. So I'll just write this down. This is going to be proportional to I goes from 1 to N, P theta I, given theta naught, sigma, and I need to multiply by my prior on theta naught. Take that. This is some normal. If I want to figure out what the full conditional is for sigma squared, it only appears here. How many times is this function being producted up? It's getting hit by both of these products, right here. If I want to learn the sigma, well then that only pops up in this part, and it's not affected by that product. So be very careful. How do I do it? I just think about the process, how everything's generated. I write it down notationally, and then eventually I write down everything is proportional to this stuff. In our full conditionals, everything is proportional to a different chunk of this. Okay. Maybe we have enough time for this. If we don't finish this, we'll finish it on Monday before we get to yes/no meetings. So the Wishart is conjugate. You're going to do something very similar to this with your RAT application. Same sort of calculation that's going to go here. Let's just work with xi's come from a multivariate normal. Multivariate. I'm going to say it's centered in mean mu. So I'll say this is mu1 down to mu k. Yeah, k. That's the dimensionality of the problem. So this is also a k by 1. This is going to be a k by k. I won't put any special constraints on anything. I'll just let it be dense. That's the way it is in the RAT problem. And so up until now, we've been making something proportional to the identity, and it's made our integration particularly easy. And so I'm going to say I've got n data points. So let me write down what the model is. So the model is just this. I'll write it down mathematically. This is going to be proportional to sigma inverse 1/2 e to the minus 1/2 xi minus mu transpose sigma inverse xi minus mu. If you want me to write in the 2 pi's, I can do that. So 1 over root 2 pi. This will be raised to the k power. We can write down equal. So my likelihood function for all of this data is going to be the product over this. I goes from 1 to n, since everything is IID. Usually I just get rid of this part. So the likelihood is proportional to that. Right there. If I were doing inference on mu, that's a constant. But if I were doing inference on sigma, now I need to have that determinant term. Okay, let's go back and look at what a Wishart looks like. The question is here, can you recognize that these are the same? Probably the answer is no. So you probably need to work on this for a while. So for one, we have a trace sitting right there, and I don't have a trace written down here. But I want to point out to you that this thing right here is a scalar. So I can drop the trace in here. Trace of scalar is the same thing. So what's the trace of matrix, the sum of the diagonals. Think of the sum of the eigenvalues. There's a lot of ways to express it, but the trace of the scalar is just that scalar. So I can drop this trace in here. I want to get my sigma inverse over on one side of this, and I want to make this thing a matrix on the other side. It's a matrix right here. So there's an identity that you used on your homework where you were able to permute the matrices around in a trace. We're going to apply that. And the last bit that I'm going to apply is I'm going to take that minus sign and I'm going to drop it right there. Turn this one into a plus. And if you don't know that you can do that, we'll have a very brief discussion about it. But ultimately, go home this weekend and convince yourself that I can drag my powers in and out of a determinant. I didn't have you prove that one. But we've done everything we need to make this look like this thing. And that's what we'll do next time. And we'll recognize that the conjugate prior for sigma inverse is Wisharts. So we'll just chisel away at that, and then you'll apply it to that rap problem. Okay, you guys, enjoy the weekend. We'll pick up with a conclusion on this. We'll write down, ultimately, what the give sampler looks like. You won't do all the details, that's your homework. And for your next homework, you're going to implement that give sampler. You're going to code it up. That's it, guys. Thanks so much. Enjoy the weekend.